Hello and welcome to this lecture on fundamental of electric drives. In the last lecture, we were discussing half control converter fed DC motor drive. We will continue from that. Now, let us look at the circuit diagram. Now, this is the circuit diagram of a half controlled converter. We have 2 SCRs and 2 diode, and this is feeding the armature of a DC machine, separately excited DC motor. So, the armature consists of the resistance part, the inductance and the back EMF, that is E. Now, as we have seen before, this can operate in 2 different mode, that is the discontinuous current operation and continuous current operation. So, first of all we will see the discontinuous current operation that we are discussing in the last lecture, that we trigger the SCRs, say for example T1 at an angle alpha. This is the positive half cycle. So, we trigger the SCR T1 and the SCR is forward biased because we have the positive at the anode. So, this goes into conduction and the current starts from 0 here. The current here starts from 0. So, and then this is the equation. When the SCR goes into conduction, the conduction this side is positive and this side is negative. So, this SCR is forward biased and this diode is forward biased. So, we have the conduction through one SCR and this basically through the armature, then it returns back through the diode. Let us say we call this to be D1. Now, when this SCR T1 and the diode D1 are conducting, the input supply is available at the output armature, that is VA. So, this is the duty interval we have triggered at an angle alpha, and the equation is VA, the armature voltage is equal to the resistance drop, the inductance drop and the back EMF, and that is equal to the supply voltage, that is Vm sin omega t, because the input is the AC supply, that is Vm sin omega t. Now, this equation is a first order differential equation. So, we are familiar with this equation. So, if we solve this equation, we get the transient part, this is the transient part here, this is the steady state part here, and we also have a transient part. The transient part is this one. So, this is a very well known solution. Now, we have to Z is the impedance of the armature circuit, that is the resistance plus the reactance, and theta is the impedance angle or the power factor angle. Now, the current starts from 0 and it reaches at some value at alpha equal the omega t equal to pi. The omega t is in the x axis. So, we have the omega t in the x axis here. So, at pi this reaches the value that is I A pi. So, at omega t equal to pi, the current is I A pi. So, if you substitute this in equation 1, we will have I A pi is equal to omega t is pi. So, omega Vm by Z sin pi minus theta minus E by R A, and we have E by R A minus Vm by Z sin alpha minus theta, then exponential pi minus alpha into cot theta. Theta is this tan inverse of omega L by R A. Now, this is, and then from pi to this equation is valid for the duty interval, that is from alpha to pi. Now, at pi the voltage will try to become negative. So, this will be prevented by the diode. We have the diodes here, 2 diode, this is D2 and this is T2, the SCR T2, and from the angle pi to beta there will be freewheeling, because we have some inductive current here, and the inductive current has an energy. So, the energy will be freewheeling through the diode D1 and D2. So, the voltage V A will be equal to 0. So, this voltage is equal to 0 and the current will decrease. Why will the current decrease? Because this current is opposed by the back EMF, that is equal to E. So, the back EMF will be opposing this current. So, the current is being opposed by the back EMF. So, the current will be decreasing exponentially. So, this is how the current will be decreasing. So, that interval is called the freewheeling interval. Now, in the freewheeling interval we have a simpler equation, and then if we substitute the value of this constant A, which is evaluated when we substitute at omega t equal to pi, I A equal to I A pi. So, we get the final equation of the current for the freewheeling interval, which is of this nature. Now, at omega t equal to beta, the current is again equal to 0. At this point the current is equal to 0 at an angle beta. So, we can substitute this here and we will get I A equal to 0. So, this is equation which involves sine and exponential. So, this is I A pi, and I A pi we have already evaluated. The expression of the I A pi is given in equation 2. So, we can substitute the value of I A pi from equation 2 in this equation, and this equation is a transcendental equation. The equation 6 is a transcendental equation which involves sine functions and exponential function. This is not an algebraic equation. So, we do not have any closed form solution for beta. We want to evaluate at what point the current comes down to 0. So, that cannot be evaluated in a closed form with a closed form solution. So, the value of beta has to be found out iteratively. So, this equation 6 has to be solved iteratively to find out the value of beta. Now, let us see the average voltage. Now, what is this average voltage? Now, we have seen in this voltage waveform that we have the back EMF E here. The back EMF is E and the voltage is V A is armature voltage and the current is armature current. We would like to find out what is the average armature voltage V A. Now, we have to integrate from alpha to pi and then from beta to pi plus alpha, because the voltage is 0 between pi to beta. So, the armature voltage is 0 because there is a freewheeling here, the freewheeling is taking place here. So, between pi to beta the voltage is 0. So, we do not have to integrate. So, integration is basically from alpha to pi and then beta to pi plus alpha. So, this we will see here. So, the average output voltage is equal to alpha to pi V m sin omega t d omega t, and then from beta to pi plus alpha the back EMF E and d omega t. Now, let us see what we get here, that is equal to 1 by pi. Now, this is V m into cos alpha plus 1, and the second term will be the back EMF pi plus alpha minus beta. So, this is the armature voltage. Now, we know that in the armature circuit what we have here is the resistance, inductance and the back EMF. So, R A, L A and E, and we have applied here the armature voltage V A, which is the average value. The average inductance drop is 0. So, we can write down here that the voltage armature voltage is equal to R A I A, capital I A, that is the although the instantaneous voltage is current is I A, the average value is capital I A, plus E, the back EMF is. The drop across the inductor, the average drop across the inductor is 0, because the inductor is an ideal inductor, does not have any resistance. So, the average drop across the inductor is 0. Now, our objective is to draw the speed torque characteristic. So, we get the value of V A from the above equation. So, we can substitute that here, that is V m into 1 plus cos alpha by pi plus E into pi plus alpha minus beta by pi is equal to R A I A plus E. Now, we can rearrange this equation, we can take this to the right hand side or to one side, and then we can simplify this. So, what we get is the following: E into pi plus alpha minus beta by pi minus of that plus 1, that is equal to V m 1 plus cos alpha by pi minus I A R A. Now, if we simplify this, what we get here is E, and then pi will cancel. So, we get here beta minus alpha by pi, that is equal to V m 1 plus cos alpha by pi, and we know that the torque equation is K phi I A, or we can say that the current I A is torque by K phi. So, this we know. So, we can substitute the value of I A here. So, that is equal to minus R A T by K phi. So, the back EMF is K phi omega m, that is equal to V m into 1 plus cos alpha by beta minus alpha minus R A T by K phi into beta minus alpha, pi is in the numerator, or we can say that omega m is equal to V m into 1 plus cos phi by K phi beta minus alpha minus R A T pi by K phi whole square into beta minus alpha. So, this equation represents the torque speed characteristic of half control converter fed separately excited DC motor. Now, this is for discontinuous conduction. So, this is for discontinuous conduction. So, when the current is discontinuous. Now, what happens if the current is continuous? Now, if the current is continuous, the flow is maintained and we get a different kind of waveform, the voltage and current waveforms are different. So, if we take continuous current case, continuous current operation, so what we can get here is the following. We have the voltage, the rectified input voltage, and here we are triggering at an angle alpha. This is pi, and here we have pi plus alpha. So, at this instant we trigger SCR T1, this instant at pi plus alpha in the negative half cycle we trigger the SCR T2. So, this is the origin 0 and we have omega t in the x axis, this is 2 pi. There could be some back EMF, but usually for continuous conduction the speed is low and the back EMF is on the lower side. So, this is E. So, the current waveform is continuous. It means the current starts from some value here and then this goes like this. So, this is the nature of current. Current never goes down to 0 here. So, what about the voltage waveform? When we trigger at an angle alpha, the voltage waveform becomes the input voltage. At alpha we have freewheeling, alpha to at pi we have the freewheeling, start of the freewheeling interval pi to pi plus alpha. Then we have the next SCR is triggered and the voltage waveform is of this sort. So, if you take a steady state nature, so the voltage waveform is periodic. So, this is the armature voltage and we have this is the armature current. So, in this case we have the output, in this case the average output voltage V A can be evaluated in a straightforward fashion, because we do not have any back EMF here, we do not have any 0 current interval. So, in that case we can integrate here just from alpha to pi, from alpha here to pi, because from pi to pi plus alpha the voltage is 0, this voltage is 0 here, again from 0 to pi also voltage is 0. So, we just have to integrate from alpha to pi. So, when we integrate from alpha to pi, the input voltage, the input is V m sin omega t over this d omega t. So, what we get here is 1 by pi into 1 plus cos alpha into V m, or we can rewrite as V m into 1 plus cos alpha by pi. So, this is the output average voltage for continuous conduction, and continuous conduction happens for low value of speed. Now, if we draw the torque speed characteristic for continuous conduction, we have a simpler equation here. So, this is equal to I A R A plus the back EMF, or we can write here omega m is equal to V m into 1 plus cos alpha by pi k phi minus T R A by k phi square. So, this equation is valid for continuous conduction. Now, let us compare these two equations. Just previously we saw the equation of speed and torque relationship for discontinuous current conduction. This is the equation, and for continuous conduction we have this equation. So, we can draw the torque speed characteristic. Now, one thing we can observe, what is the range of alpha here? So, the range of alpha is actually from 0 to 180 degree. This is the range of alpha, and for full range of alpha the voltage is always positive. This voltage for continuous conduction is always positive. So, it means in case of a half control converter, the average armature voltage can never become negative. So, this is a one quadrant converter, this can operate only in one quadrant, because the average voltage cannot be negative here. there is a freewheeling path. So, the voltage will come down to 0. Now, here if we draw the torque speed characteristic, we take the help of this continuous conduction case, that is this equation. So, these are the straight lines for various values of alpha. Let us say this is the first one, then we have second one, second value of alpha, we have the third value of alpha, and continue like this. So, this let us say this is alpha equal to 0 and this is alpha equal to 30 degree, alpha 60 degree, alpha 90 degree, alpha 120 or and so on. And as we have already seen, this is the speed in the y axis and torque in the x axis. And for low value of torque, the speed, the equation will be governed by some other equation, which is the discontinuous conduction. So, this dotted line represent discontinuous conduction, and so on. So, this is the boundary between continuous and discontinuous conduction. Even for alpha equal to 120 also we have discontinuous conduction. So, we will have some no load speed. So, this region is for continuous conduction, and this region is the discontinuous conduction. And for the discontinuous conduction, we have the equation, that is this equation. So, if I call this equation A, let us say this equation A is for the discontinuous conduction and equation B is for continuous conduction. So, this is governed by equation B and this are governed by equation A. So, now the no load speed for discontinuous conduction will be for alpha from 0 to 90 degree. This is V m by k phi, V m by k phi. This is the no load speed. So, we can write here that no load speed for alpha greater than 0 and less than 90 when the conduction is discontinuous is given by omega m naught, that is equal to V m by k phi. So, when the conduction is discontinuous for no load, it means when we are talking about no load condition, torque is 0. So, how can the torque be 0? The torque can be 0 provided the current is 0, because we know that torque is a function of flux and current. So, when we say that torque is 0, it means the current has to be 0, because we have a separately excited DC motor. And when the current is 0, it means the back EMF is the maximum possible value, that is V m. So, when the back EMF is V m, E is equal to V m, naturally the no load speed is equal to V m by k phi. So, that is the no load speed for alpha between 0 to 90. Now, if alpha is greater than 90, the no load speed is given by this equation. No load speed in this case is given by V m sin alpha by k phi, because V m sin alpha will be the maximum value of voltage that you can have when alpha is more than 90. So, the back EMF should be equal to the maximum possible armature voltage, that is V m sin alpha, to make I A equal to 0. So, now in this case we have the motoring. So, the motoring is a straightforward case. So, for motoring we have this half control bridge where we have thyristor and diode, and this is the armature circuit. The field is separately excited. This is single phase input here, AC input. So, this is the motoring case. We have the voltage here, that is V A. So, for motoring what we have in this case, that V A is positive and the current is positive and speed is positive. Now, when we talk about the braking, in this case the braking is not directly possible. So, what we have to do here, for braking we have to reverse the back EMF. Now, when we reverse the back EMF, braking will take place, and in that case we have the same converter circuit, half control converter. We cannot achieve regenerative braking here. So, in this case the back EMF has reversed either by reversal of speed or by reversal of field. So, if suppose the speed has reversed, initially we have omega m is 0. So, in this case what we have here, omega m has reversed. So, if omega m has reversed, the back EMF will reverse, because the field is separately excited, field is constant here, and we have the armature is supplied from AC supply. So, we have the voltage V A in this case. Now, this V A is coming from the converter. So, the current is still in the same direction, because we have the converter circuit. The converter can only allow the current to flow in one direction. So, what we have here is V A is positive, the current is positive here, the speed is negative, and the power of course here is negative, P is negative. The power is negative. So, this is the braking in this case, but unfortunately the power in this case cannot be fed back to the supply. The mechanical power is negative, P m is negative, because the torque is positive, but the speed is negative. Here earlier we had torque positive and speed positive, but in this case we have torque positive, but speed is negative. The mechanical power is negative. In the earlier case the mechanical power is positive. So, this type of braking is called plugging, and this is the reverse plugging, because the speed has reversed. So, in case of a half control converter, we cannot achieve regenerative braking, because the converter cannot reverse the voltage, neither the current can be reversed. So, the braking energy here, when the motor is being braked electrically, the braking energy is wasted in the armature resistance. So, this is the limitation of half control converter. We have forward motoring, but we can only have reverse plugging. So, we conclude that today's lecture will continue in the next lecture.